We're now going to look at magnetization in materials, and the basic idea here is very similar to polarization of materials in an electric field. And so we're going to take the same sort of basic approach by looking at just a simple atom with a nucleus and electrons around it. So what we know is that in an atom, we have electrons. So let's say in an atom, we have electrons which are moving around the atom, around the nucleus. So electrons move around our nucleus, and they're also moving around their own axis. And they're moving around their own axes, and so that's just the spin up or spin down of the electron. But basically, if we forget the spin up and spin down and we just focus on this electrons moving around the nucleus, what we have then is we have moving charge. And so of course, if we have moving charge, we know that that can induce an not an electric field, a magnetic field. So we're going to say that this creates some internal magnetic field. So creates an internal magnetic field. And so let's call that magnetic field B sub I. And so just to draw sort of briefly pictorially what we're talking about, of course we have some nucleus here, which is mostly positive charge, and let's say we have some electron out here, so this is a negatively charged electron, and let's say we have some path around here that looks something like this. So our electron is moving around this path. Now, of course, that is greatly oversimplifying things, but it's going to give us a good, at least approximation of what's happening. So we're saying that this is approximately equivalent to having some current path, which is the same path of that electron, but of course our conventional current flow is in the opposite direction. So, oops, don't want to erase that. So of course our current direction would be in the opposite direction. So this would be some internal current I sub B, which is due to that electron movement. And from our right-hand rule, we could say that that is going to induce some magnetic field, which is going to be coming up through this loop. So we would have this B induced, or B internal rather, and of course we'd have the other field lines that look something like this. And so we could draw any number of field lines there. But the main point is that we do have some internal magnetic field. And so we could find what the equivalent magnetic moment is. So our equivalent current loop, which is due to that electron moving around the nucleus of the atom, has some magnetic dipole moment, M, which is equal to that I sub B times the loop area S and a unit normal vector U sub M. And again, the S is our loop area, as I said just a second ago. So what we're going to see is if we have no external B, so no applied external magnetic field, B, then what we're going to have is that the sum of M in a material is going to be approximately 0. So the sum of all of our magnetic dipole moments, M, in a material is approximately 0. And so the reason for that is we're going to have our random orientation of atoms and therefore of our M. So random orientation of atoms and consequently of our magnetic dipole moments. And so what that might look like is, in this case we had our electron path shown here. Maybe in another one we have our electron path in this direction, and that's going to give an M in an opposite direction. Maybe we have some other one like this, something like this, with the electron moving counterclockwise as opposed to clockwise. So basically we have all of these M's pointing in opposite directions, just sort of randomly, and sort of law of large numbers, if we have enough of these and we sum them, that's going to be approaching 0. And so what we can see though is if we then apply some external B, we're going to force all of those magnetic dipole moments to align in one direction. So applying an external magnetic field B is going to cause those magnetic dipole moments, so M, let's say M's, to align with that external field B. And so once we have that, then our net magnetic moment is no longer going to be approximately 0. So net magnetic moment is no longer 0. Okay, so let's see if we can quantify that with some equations. And so in order to do that, we're going to define a new parameter as well, similar to how we defined polarization for our electric field effect on materials. We're going to define magnetization. So magnetization. And so we're going to define that as M, capital M, as opposed to lowercase m, which is dimensionally going to be equal to amps per meter. And so what this is going to be is ultimately this is going to be equal to the magnetic dipole moment per unit volume. So again, very similar expression as to what we talked about with polarization. So magnetic dipole moment per unit volume. So let's extend that to some arbitrary volume. So let's say we have N atoms in some volume delta V. So for N atoms in some volume, which is given by delta V, so some differential volume, then we could say that our magnetization, capital M, is going to be equal to the limit as that delta V is going to 0, so as that differential volume is becoming very small, of, in the numerator, we're going to be summing all of our individual magnetic dipole moments. So this is from k equals 1 to capital N of m sub k, so lowercase m, divided by that differential volume delta V. And so what we notice is that if our m is not equal to 0 everywhere, then our material is going to be magnetized. If this sum is equal to 0, then we're back to this case of no external field, and we see that we have this random orientation such that everything is approximately canceling out. Okay, so we're not going to go through the derivation of this, but again, we can show some similar things as to what we saw with polarization. So we can use our magnetic vector potential. So using our magnetic vector potential, which recall is just A, and with some vector identities as well, what we can show is that our magnetization is going to result in some current densities. So magnetization results in, so we're going to have two current densities associated with this, the same way as we talked about charge densities when we were talking about polarization. So we have our J sub B, which is equal to the curl of our capital M, so the curl of our magnetization. And so this is going to be our bound volume current density. So bound volume current density. And you'll also hear it called our magnetization volume current density. So instead of bound, you might see magnetization volume current density. And we also have a bound surface current density, and so that's going to be K sub B, which is equal to M cross the unit normal vector. And so this is going to be our bound or magnetization surface current density. And so for more details on how we can get those from A, you can look on page 370 in the textbook. But again, it's not going to be too important. And really, we're not even going to get into using these equations too much, but I at least wanted you to see them to be familiar with them. And as I mentioned, there's of course a clear analogy here between our bound volume and bound surface charge densities. So clear analogy to our bound surface charge density, rho sub PS, and our bound volume charge density, rho sub PV, that we looked at previously. And so you can see that on page 5-9 or on page 189 in the textbook. And so of course that was for polarization. So a couple other sort of notational things is that our capital M, our magnetization, is also sometimes called our magnetic polarization density. So also called our magnetic polarization density. And then, of course, in that sense, it's analogous to our polarization with our electric fields and our materials. However, we also want to keep in mind that it is somewhat analogous to our magnetic field intensity H. And the reason I say that is because if we come back up here, we see that it has the same units of amps per meter.